Hi, I'm Derek Kubo, and I'll be talking about the basics of analog signal processing and transmission. So we'll start off with defining an analog signal, and I'm going to do that by showing some examples. This is a pure sinusoidal signal with respect to time, voltage versus time. I've denoted it as a continuous wave signal. Its frequency domain response, power versus frequency is shown here, where all the energy in this analog signal is confined to one frequency. Here's a small modification to the CW waveform. This is amplitude modulation, where we take the voltage waveform and modulate it with an external signal, be it voice or music for the AM broadcast band. The spectral response is shown to the right here. Still has a carrier, but it has a modulating sidebands associated to the modulation signal. Here's the FM. So this is frequency modulated signal. Note the amplitude voltage is constant, but the frequency is being modulated in this case from low to high to low. It has a similar spectral response where the carrier is present, but then there is a modulating sideband varying around it. The analog signal that's most applicable to us is this noise, random noise that has a random variation in amplitude and frequency as a function of time. And its spectral response is shown here with an ideally flat response and a low frequency and high frequency cutoff. The amplitude not shown here is should be Gaussian in distribution, and that's kind of typical of what we see in our radio astronomy type of application. So how does that analog signal differ from a typical digital signal? And I explain that by using a portion of an analog signal and sample it at regular intervals of t sample and assign, this is still voltage, but I've assigned 8-bit quantization. So this is an 8-bit A to D conversion of an analog signal to digital. Starts with all zeros, excuse me, on the low negative level. This could be -1 volt. Here, the mid-scale is 0 volts, represented by 1 in all zeros, or 128 decimal. And at the top, I have 1 volt being represented by all ones, or 255. Sometimes this is denoted as offset binary because the mid value is assigned to 0. Negative values are the values below 128, positive are above 128. And the digital output, I've serialized the first 4 digital words here as 4 sequences of digital 8-bit words, and its bit rate is RB. It's 8 times the sample rate R sampled. It's 1/t sample. And it has a spectral response as shown here, where power versus frequency, it's a sync function or a sin x over x function, where the first null occurs at RB. So if you had 10 megabits per second, this would be 10 megahertz, and this is DC. So this hopefully differentiates, at least qualitatively, the difference between a digital serial stream of data, which actually only has 2 values, 1 and 0, and an analog where you have a continuously varying signal. Okay, so why do we still use analog signal processing after all today? Most of the new developments are with digital signal processing. Most of your cell phones, digital satellite communications, digital. But the reason is that the signal coming into the antenna is of analog nature. The receiving antenna is usually followed by a combination of low noise amplifier because the signals more often than not weak because it gets attenuated by traversing through the ether. And we also perform analog filtering very early to reject unwanted signals. For instance, a cell phone, it's receiving Wi-Fi and everything else that you have in your vicinity, and it could overwhelm the front end. So analog filtering, and we do heterodyne frequency conversion to some common intermediate frequency. Cell phones operate 900 megahertz Wi-Fi at 2.4 gigahertz and 5 gigahertz, and that's usually down converted to some more easily manageable frequency. Digitization is generally performed as early as possible to avoid any distortions caused by analog signal processing. We typically perform digitization at IF, but sometimes you could do it directly at RF after the LNA. For instance, at broadcast band AM and FM radio can be digitized directly and then processed. For radio interferometer telescopes, we require the generation of a very low noise local oscillator, which we send out to each of the antenna. And first heterodyne down conversions performed in the antennas. For the SMA, we operate at 200, 300, and 400 gigahertz. There's no way we would digitize at that frequency. So we do down conversion after mixing with this pure LO that we develop and send out to the antenna. So definitely analog signal processing is necessary today. We do live in an analog world, and so everything that we interface to is analog, but in terms of processing, we often do it in the digital domain. So the basics of analog building blocks. So we're going to start to go through the fundamental building blocks of analog processing. We're going to start off with the transmission line. So the characteristic impedance of everything that we work with in astronomy and in industry is 50 ohms, and it's a compromise between loss of cable and power handling capacity. So 50 ohm source, a voltage source is normally 0 ohms, but we follow it with a source impedance of 50, and then the transmission line is defined to be 50 ohms or as close to 50 ohms as possible. That means V over I is, or voltage over current is 50 ohms. And then we send that signal to a 50 ohm load. And everything is ideal, everything would be matched. Okay, here's some examples of 50 ohm transmission lines. Here's straight waveguide. It's rigid, can't be bent. Here is a semi-rigid coaxial cable. Here's flexible cable. And here's Heliacs cable. There are different kinds of cables. This one happens to be very large diameter, about 1 inch in diameter. It's corrugated, so you could bend it a little bit. The outer conductor separated from the inner with a helicoil, so the dielectric is actually air. It's very low loss. This particular one only operates to 1 gigahertz, so it may be useful for cell phone or cell towers. You typically see this if you look at a cell tower. There's these black cables going up from the ground where the transmitter resides, and then the antenna on the top. Still on transmission lines, we use transmission lines on circuit boards. So even PCs and cell phones use 50 ohm transmission lines on their circuit boards because it's essentially RF being sent down these traces. So instead of coax, we use microstrip often. There's a ground plane at the bottom. There's some dielectric material, low loss dielectric material, and here are the E fields and H fields. Here is a microstrip transmission line on a substrate. Connectors would normally go on both ends. Here's a different version of transmission line through circuit board. There are more than just these two. There are several, but I just show the two common ones. This is strip line, where the copper trace is embedded between two copper plates or conductors. And it's well shielded because there's no exposure to the outside, but it's difficult to interface to because we usually put components on the top or the bottom layers. Okay, so still talking about transmission lines, you'll probably come across this term at some point, VSWR. So that's voltage standing wave ratio. And that's an indirect way of characterizing how much of an incident wave gets reflected back. Its fundamental parameters rho, the voltage reflection coefficient. So this would be a boundary between, say, an antenna and a coax, or coax and an LNA. They all have non-ideal impedances that deviate from 50 ohms. So a portion of the signal gets reflected back, and that is represented by rho. So if rho were 0, then 100% gets transmitted. If rho were 1, then 100% gets reflected. And VSWR is a historical legacy terminology. It used to be measured this way. That's why it was called voltage standing wave ratio. And you back calculate for rho. But today we use return loss to measure reflection coefficient. So we measure 20 log rho. Okay. And so why is that important? Why is VSWR important? Because generally we have multiple interfaces. We have an antenna, an LNA, a filter, and just a number of components that are in cascade. And each interface boundary condition has a non-ideal rho that's non-zero. So let's just go through and we traverse from left to right. We have a transmitted waveform, these of 1 of t, and it's a vector. And then we have a portion of it being reflected and reflected again. So it has to go through this L 2 times. And we arrive here with V2 transmitted. So these two are vectors, and then they create constructive and destructive interference. And you can see it in this next plot right here. I did an experiment where I have a 7-inch coaxial cable, and I purposely loosened the connectors to make rho large enough so that you could see it. And then I measured the response from 10 to 20 gigahertz. And one can calculate the standing wave interference pattern by this relationship, F ripple equals the velocity through the coax, so speed of light divided by epsilon, square root of epsilon, the dielectric material, which is Teflon in this case. And then 2 times L, because the reflected signal goes through that coax twice. It goes backwards 1 and then forward 1. So that's 2 times L. And so I calculated it based on 7 inches and 568 megahertz. I measured it, marker 1 and marker 2 here, between the 2 peaks, and I got 5/70. It's negative because I have marker 1 on the right of marker 2. And so here is something that's really undesired. Ideally, it would be kind of a flat response, higher loss at higher frequency, but not this ripple. If I tighten the connectors, this basically goes away. But the point I wanted to make was there are 2 important things. The magnitude of the reflection, or the value of the reflection rho, determines the height of the standing wave, but the frequency of the standing wave is a function of the length. So if I had 0.7 inches instead of 7 inches, well, this number right here in meters gets shorter by a factor of 10, and then that frequency becomes 5.7 gigahertz instead of 568 megahertz. And so you have a slower moving ripple going across the passband of interest, and that's more desirable than rapidly moving like this. So our goal is to minimize rho and to keep the interconnects as short as possible. We see later that we could do that by, we could at least reduce L by going to circuit board designs. So I'm going to rip through quickly the basic analog building blocks that we typically use. The first one's the directional coupler. You come in on the left, and a portion of it gets sampled off. In this case, it's a 10 dB coupler, so 10% gets picked off and 90% goes through. Here's the internal equivalent. It's a Lang coupler design. It's bidirectional device. Okay, so a power divider. I show a 4-way power divider here, but in the photos, a 2-way power divider. This is a Wilkinson power divider design. There are many sections in here to increase the bandwidth. Um, a signal coming in gets split to two equal signals, each half the power of the input. So there's a 3 dB loss at the output. A 90-degree hybrid coupler. You can also get 180-degree couplers. This is a 90-degree branch line coupler equivalent. It's microstrip. You can see there's a circuit board sandwich between two grounds right here. So it might be actually a strip line in this case. Here is a chip version of a hybrid coupler. It's often used in IQ modulation, demodulation, and IQ down conversion for sideband separation. Here's a fixed attenuator. We use these to control power, but also to accommodate for mismatch between components because you could reduce the reflection size by adding attenuation. Here's a chip version. Next is a variable attenuator. We use this for signal leveling. Almost all receivers have some kind of level control that you can vary the gain dynamically. Here's a waveguide version, manually controlled. Here's an electrically controlled, digitally controlled variable attenuator. Here is a gallium arsenide mimic. It's a monolithic microwave integrated circuit. It's a small chip. We actually use this in the SMA. Next item is a power detector. Just as it sounds, RF radio frequency signal comes in on the left, and out comes a proportional DC voltage. We use this to measure power within our circuits. Circulator, this is an interesting device. It's a ferromagnetic. There are two magnets about this microstrip or strip line type of design. And just to explain, you come in on the left port, you go in the clockwise direction, you come out on port 2. If you came in on port 2, you clockwise again, come out on port 3. And if you came in on port 3, you would come out on port 1. It's used for isolation between two mismatched components because the signal can't get back to port 1. It'll come out on 3. And if you terminate it, that signal just goes to a load. Here's a connectorized version. Some filters. Here's a symbol for a low pass filter, but there are band pass, high pass, band stop. There are many different kinds. It's generally filters are represented by lumped element Ls or inductors and C capacitors. This one happens to be a Chebyshev design, 3 sections. So on the right, we have a 5-section lumped element filter. And you can also make filters without capacitors, inductors by having cavities or resonant cavities. This is a waveguide resonant cavity. You can tell by the slugs here where you adjust the cavity resonances. Here's a connectorized cavity. Here is a coupled line filter that you print using microstrip on a circuit board. And here is the equivalent passband response. So it is a bandpass filter with 1, 2, 3, 4, 5 sections that causes number of sections is proportional to the steepness of this stop band. You can see this blue trace is 20 log rho, or the reflection coefficient. So almost all the signal gets reflected here, and that's why it's a stop band. You get to the pass band, most of it doesn't get reflected, and then back to the upper frequency where almost all the signals rejected. Mixers, this is a key component as the other components used for frequency translation, down conversion or up conversion. Here is the schematic equivalent for a double balance mixer, excuse me. And topological layout. Here's a waveguide mixer, connectorized mixer, and a gallium arsenide mimic mixer. Amplifiers, everything we spoke of before this was lossy components, so we have to make up for it by using amplification. There are different types of amplifiers. The 2 typical ones are power amplifiers for transmission and low noise amplifiers for reception. Many amplifiers that we use in astronomy are cryogenically cooled. Here is a connectorized version, a mimic version, waveguide version. And finally, for building blocks, I'm gonna list this as a local oscillator. Here's a waveguide version, surface mount version, connectorized version. there are two fundamental types. There's a free-running oven-controlled crystal oscillator, but we usually use phase lock sources where a low phase noise reference comes in. So that'd be the station reference, 10 megahertz typically, generated by some very low phase noise source. And this is generally multiplied up using a phase lock loop and some dividers to produce high frequency outputs. Now, this is a spectral response of a CW waveform that we use on the SMA for one particular antenna. This one's at 8.45 gigahertz. It's like the first plot that I showed on this talk. It's a frequency versus power, and almost all the power is contained here. There's some residual noise. The shape is indicative of the phase lock loop bandwidth. You can see this kind of a hump that occurs here. Okay, so that's the end of the analog building blocks, a subset of them. There are a lot more. I maybe covered just a small fraction of what's available, but using these, let's see what we can build from a practical standpoint. So the first example I have here is the YTLA project on Mauna Loa. It's an 86 to 102 gigahertz receiver. So there's an antenna that focuses all the energy into the waveguide horn. So that's that guy. A directional coupler, we talked about that. Orthomode transistor separates the two linear polarizations that come in, and we didn't talk about that. You can't see it actually here. But then the LNAs, low noise amp, circulator, low noise amp, circulator, and these are for isolating the impedance mismatches between the two amplifiers. Amplifiers typically have a relatively poor mismatch, so we use isolators so that we don't have that undesired standing wave that I showed earlier. Finally, right before it leaves the receiver cartridge in the warm section where it's not cryogenically cooled, we have a mixer that down converts 86 to 102 down to 2 to 18 gigahertz, so more manageable. It's difficult to digitize at these frequencies. We couldn't do it today, maybe someday in the future, but that's what heterodyne down conversion is for. Transmission of an IF signal from the antenna to the correlator room, which is hundreds of feet away for the SMA. This one was developed but not made yet. So we come in on the left from the receiver, 0 to 4 gigahertz, amplify, variable attenuate, amplify, couple off so we can measure signals. We can use that to feedback and control the automatic level loop. And then we transmit the signal to from the antenna to the correlator room using a fiber transmitter. This is all microwave circuit board designs, very small, compact, only about 3 or 4 inches in width. So that solves a problem of having long L between these components. Here's something that we actually did build. It's a frequency translation from, excuse me, from IF to baseband. So we have multiple blocks. These are IFs, 2 to 4, 4 to 6, and so on. This particular down converter takes 2 to 4 gigahertz bandpass filter, mix, low pass filter, and goes to an ADC for digitization. Here you can see the actual block diagram. Here's a low pass filter. There's 2 channels. Mixer, low pass filter, amplifier, variable attenuator, amplifier, and then the ADC or the A to D converter would be outside of this assembly. We're going to make 8 of these 16 channels for our 8 antennas. Here's another block down converter that we subcontracted. It's all on circuit board. We take 12 to 14 and 14 to 16 gigahertz. It's too high for digitization, so we down convert to baseband. So you could see the signal comes in here, gets split to 2 bandpass filters. Bandpass filters comes out, goes in, gets down converted with these white mixers. Low pass filters, gets variable attenuated here, and then the output to the ADC. So the ADC is not part of this assembly, it's outside. The last thing is the transmission of our ELO signal for the Greenland Telescope project, which is in Greenland. So the transmission, we generate a 18 to 32 gigahertz signal, starting off with a hydrogen maser, just like the SMA, we have one up at Mauna Kea. It generates a very low phase noise 10 megahertz signal that gets sent through some coax to a low phase noise synthesizer in this case that produces anything between 18 and 32 gigahertz. It goes to an optical transmitter that sums this output with 2 other references. And then that gets sent out to the antenna through a long fiber. Right now it's only a few hundred meters, but it will be several kilometers when we get to our final destination. On the other end of that fiber is a fiber optic receiver in the antenna receiver cabin. The signal comes in here. And here's a spectral response plot of the CW-LO signal before it's transmitted. And here is after it arrives at the telescope itself. It gets degraded slightly, but they're almost similar. And so that kind of concludes the talk of analog signal processing. Hopefully you learned a few things, if not just visually appreciate some of the technology that goes behind the telescope. And hopefully you get a package of this presentation. If you could look up the references to find out more information about each of the slides that I have presented here. So thank you very much for listening in, and I hope you have a good class following this. Thank you very much.